Hey, hi, this is Vivek, and today we're going to talk about multiple different problems that we can solve in number theory, right? So, in the last video, I talked about AX plus BY equal to C, this very fundamental equation that how do you find the solutions for this, a single solution, multiple solutions, when is there a solution, and things like that, right? Now, directly, this equation is helpful for many different things, but again, if you go beyond that, also there are multiple different problems that appear again and again, like linear equation, right? Linear congruence equations, then things like Chinese remainder theorem. These things do pop up again and again, right? And we will try to explore what these are either through the blogs, because these blogs are really well made in the CP algorithm website, as well as we'll try to like see how maybe we can derive them from the very fundamental AX plus BY equal to C, because that's the root equation. Like if you know that equation, how to solve it, you can actually solve many different problems that might pop up from that, right? So that's what we'll look into this particular video, right? So I'm gonna assume that you know how to solve AX plus BY equal to C and how to find its general solution and other things. If you have not watched that particular video, like in the I button above, I will like add that particular thing and you can kind of go and watch that video over here. After that, you can come back to this one and then learn this particular thing, okay? So that you are ready to solve almost any number theoretical idea that pops up, right? Maybe in a separate video, we'll go through these last few things, which is discrete log, discrete log, primitive root, and stuff like that, right? So these are some things that are very interesting ideas, and maybe we'll take up them in a specific video. But these are very like rare algorithms. I have not seen questions directly asked on these, so we'll talk about these in a separate one. But linear congruence, Chinese remainder theorem are things that are pops up again and again, and there are even sometimes problems which use its idea, not just even the direct algorithm to solve it, right? So that's what we'll do today, right? So I'm gonna assume now, please watch it, please watch the video if you have not watched it, but I'm gonna assume that AX plus BY equal to C is an equation for which, given an A, B, C, you can find one solution for XY. We know that, hey, only this is solvable only when GCD of A comma B divides C, right? We can find out a solution for AX plus BY equal to GCD of A comma B. From this, we can find a solution for AX plus BY equal to C. From this, we can also find the general solution by substituting and getting the solutions of AU plus BV equal to 0. I've talked about these in that previous video. And then we can form a general equation for this, right? So this is something that we can actually do right now. Like I'm assuming that you guys know how to solve this. Like you will get a general format for this, right? General format solution for this. Like let's say the x over here, you got a solution x dash and y dash, right? X dash and y dash. So x dash into c by g. G is the GCD of a and b. This number is g, let's suppose. So this will be the one unique solution, y dash c by g. And then let's you can do a plus and a minus on this side, and then you will be able to solve the rest of the things. Like when you are putting this one over here in u, it has to be b by g, so k times b by g. Over here, when you're putting in v, it should be a by g, a by g times k. This is, let's say, the general form of the solution for this linear diamond equation. So this is something you can remember. I generally support you know how this works and then maybe remember it at times. Okay. Now today we're gonna take some more equations that pop up again and again, and a very common one is going to be inverses. Now before we start with this, there has to be one small prerequisite about terminology. There is an equation like this: AX is congruent to B mod M. Things are written this way, right? Or X inverse is congruent to A mod M. Let's suppose this is written or this is written. What are these? What does these mean? Because I think mod M is not something that everybody reads. Everybody reads unless they read about, let's say, number theory separately. Okay. So mod M basically just says that, hey, these two numbers are equal given that both are taken remainder with M. That's what it means. Hey, x inverse is going to be equal to this provided that both are taken remainder with m properly, right? So mod m basically reduces the number in the range, let's say 0 to m minus 1, right? So it's in the domain where every number lies in this range, and if you go beyond this, you kind of take subtract a m and then make it go back to that range, simply taking a remainder with m, right? And it goes back to this range, right? So this is what is assumed when you say mod m, right? When you write this, it basically says that this is equal to this given both are remainder with m. So another way to write this would be ax remainder with m is gonna give you b remainder with m. Okay, this is fine. This is true. Okay, same thing. So x inverse, I'm assuming that inverses by default are taken modulo. If not, you can write m. That's not harm over here. Is equal to a mod m, or just a maybe if a is already modded, right? So this is what these notations mean. So note this is a common notation that we will use again and again. I'll explain you multiple times at the start so that you can grasp this thing. So this is what a notation thing that you need to know about. Next, we'll kind of get into finding few problems. Number one, we'll take inverses, right? So you might know about, hey, there is something called as inverse, but why do they exist? Uh, Majorly because many times we need to find fractions, right? Whenever you're dealing with fractions, you have to have like an inverse in the equation, and those inverses is something that will make it easier to compute numerator and denominator separately. Let me explain what we are doing, right? Let's simply take n choose r, right? N choose r is this n factorial divided by n minus r factorial and r factorial, right? Now in this particular equation, if n and r are pretty large, these numbers get pretty big, right? These numbers get pretty big. So what we would like to find out is maybe like find out the numerator and by denominator and then just divide it. But the problem with that is if you find numerator mod m, okay, if you find it mod some given m and denominator mod some given m, the problem with that is now you cannot divide directly, like you cannot just do an integer division, right? If you do an integer division, it will not come out correct. For an example, just think about this, like 6 by let's say 3, right? 6 by 3 will come out to be a 2. And then if I take a remainder with 5 on both numerator and denominator, so 6 mod 5 divided by 3 mod 5 is not equal to 2, right? Is not equal to 2. Because if you just divide them like a floor division, this will come out to be 1 by 3, 0, right? Which is not 2. So instead of writing it this way, we try to write it this way. 6 mod 5 multiplied by 3 mod 5 whole inverse, right? Instead of writing this as a like something that is going to do an integer division, we make it an inverse and multiply it. It's very similar definition, right? Like x inverse in its like numerical sense is nothing but 1 by x. But since dividing by integer division is not a correct solution, and we don't want even floating point, the original number would have perfectly divided maybe, but now after taking modulo, it's not dividing. So what we do is we take an inverse, right? And this is going to be whatever there is, okay? Whatever the number mod 5, because we have taken a remainder with 5, right? That's what we are interested in. So sometimes you need remainders with mod 5 by finding out inverse of a denominator in a fraction, and that's why inverses become very very relevant. So there are multiple ways to find remainders. One is using Fermat's little theorem, like if there is prime, so a to the power p minus 1 is congruent to 1 mod p. This is something called as Fermat little theorem, which is for prime p's. Now, if you just write it this way, A inverse, or I would rather write it this way, A to the power P, okay. Now, if you see this particular term over here, think about this, A into something is 1, A into something is 1. So can I say X is nothing but 1 by A or nothing but A inverse, right? So this is a term which we will just frame as, okay, this is a valid value of A inverse. And that's how we sometimes find for modulo prime P, right? When the modulo or the remainder is from which with which we have to take, like 8 to the power 9 plus 7 is a prime, we just simply take any number and raise it to the power mod minus 2 or P minus 2, whatever prime is given in the problem, and you get the inverse of that number. But this might not always work. I mean, depends upon the problem. If this is a prime, then it works. This is always true when this is the equation which is always true when it's prime. Okay. This equation comes from Fermat's little theorem. Okay. But then we don't always want to go into this side of the equations, and we want to do it in a generic way. So what is a generic way to think about inverses, right? So I can think about this way, that A into A inverse, the main definition of inverse is A into A inverse should be congruent to 1 mod some m, given m. Okay, I don't know if it's prime or not, but I want to find an inverse. So a into a inverse, 1 by a basically in its numerical sense will be congruent to 1. So what can we multiply with this with so that we get a 1? So I can write it this way. Hey, let's say we don't know inverse, so I'm going to write it this way. Okay. Okay, this is what we are dealing with. The next thing over here is, hey, what does modulo m actually means? When we say mod m, in the both the sides we are taking mod remainder with m, right? So when we take remainder, there is a quotient m plus remainder is how we write, right? So when you take a number x is congruent to q times m plus r, let's say something like this. So you can subtract or add any number of times m, and then whatever you get is a remainder, right? So as that remainder lies in the range m minus 1 till 0. This is what we do. You can add and subtract m any number of times till you get this. Now, since over here also we have a remainder with m, and 1 is already taken remainder with m because 1 is a very small number, m will definitely be more than 1 in general cases. So the left hand side is what we have to deal with. So ax plus, you can do any number of times with m. So I can write minus also, it doesn't really matter. Okay. So what this is saying is, hey, you have ax, add or subtract any number of times the number m, which is the modulo, and you have to get a remainder of 1. Right, that's what it is saying. This equation is absolutely equal to this equation for some random value b. Okay, for some random value b. Okay, I'm gonna just rephrase this in a different way. I'm gonna say ax, okay, plus minus b, it's a variable, right? I don't know what the value of b is going to be, so let's say plus minus b, it is going to come out to some number y. Okay, plus y times m is equal to 1. Okay, this is what we are interested in. Now, if you see this x we don't know, this y we don't know, but this is the equation. Try to compare it with the equation that we know, ax plus by equal to c, right? A is known, m is known, a is known, b is known, and x and c is also known. X, y we have to find. This is a very similar equation, right? So number one, the solution only exists if divides 1. Okay, GCD of a comma m divides 1. If GCD of a comma m divides 1, which basically means it will be equal to 1, right? There is a number which divides 1. The number is 1 itself, right? So we can say that this is nothing but equal to 1. What does that mean? A comma m, GCD of a comma m is equal to 1. It basically means that, hey, the number a and m has to be co-prime. So this is a new term. Co-prime means there is no common prime factor. So GCD of a comma m when is equal to 1, it basically means a and m are co-prime. So given this equation over here, we have to find inverse. It only exists if a and m are co-prime. Note that when m was prime number, then like GCD of any number x with some prime number p such that this x is like less than p in general is always going to be like existent, right? This GCD always going to like be equal to 1 because the prime is not present in this, right? So this is what we always got in the earlier case. So there was always a solution, but this case, this has to be true. GCD of a comma m has to be 0. If that is the case, can we use extended GCD algorithm to find out a solution for this, right? So just plug in the extended GCD algorithm, not even just C version, the GCD of a comma b version, because it's equal to 1, right? It's equal to 1. Just plug in that equation and then you will get a very nice solution for this, right? You will get an x dash and the y dash value for this, right? And in fact, whatever you get as an x dash over here is a solution to this equation. In fact, the x dash that you get is the A inverse, right? So this is how you can derive even like an inverse of a number in case A and the modulos are not prime, if you think about it, right? This is how you fundamentally think about any problem, like from its definition, go till the equation AX plus BY and think about, okay, how do we get a solution for this, right? So this is how you can find inverses for general cases, right? Where prime is not there and you cannot just take a power directly. Okay. So this thing works every time. Simply think about this equation, right? The a is given, m is given. This is 1 always because we have to get a remainder of 1. Multiply gets 1. From this equation, just plug in the GCD, extended GCD's algorithm, right? And you will get the value of xy, and then x, from the derivation we know that x is nothing but x, the solution for this equation is the solution for this equation, and it's nothing but the inverse, right? This is how you can find inverses. Another important observation is it only exists when a and m are prime. Okay, so now we are done with inverses, right? Next we will move to a general equation called linear congruence, which is nothing but a times an x is congruent to b mod m. Okay, what does this mean? What does this particular congruence means? It's nothing but there is a variable x which we don't know, but a times that when taken remainder with m is going to give us b mod m. Okay, b remainder with m. That's it. Okay, this is what this is saying. When you take ax, okay, and you take a remainder with m, is going to give b. I'm assuming that b is going to lie in the range 0 to m minus 1. Even if it's not, we can always take a remainder and get it, right? So a and b are given to you. You can always take a remainder and get it in this range. You have to find a solution for this equation such that you can plug in over here and get an answer. In fact, if b was 1, then x would have been a inverse, but we have some other b over here. Okay, how do we solve this? Very, very simple flow. So ax is congruent to b mod m. We know the definition of mod m is nothing but you can add and subtract any number of times. So ax plus minus some z number of times m, right, is equal to b. So when you subtract, add, subtract, you have to just find some z so that this satisfies, right? You can add, subtract any number of times. In fact, ax plus, I will just call this as some y m equal to b. Okay, and this is very similar to ax plus by equal to c, right? This is very similar to this. It's just that in this case, a is equal to a, b is equal to m, c is equal to b for this equation. Okay, from this equation, just plug in these values in this, and you will get one value of x and y. Okay, y we don't care about how many times we want to subtract. uh, from y you will get the value of plus minus z. It doesn't matter for us. Instead, what we are interested in this x, because we will get this x, we will get this x, and in fact we'll get a solution for this, right? This is how you can also find linear congruent solutions. Okay, again over here the condition for the thing remains the same, that hey, gcd of a comma m divides b. This condition remains the same. Okay, so now once we have understood this, let's do a quick problem. I'm going to give you some time to think about this particular problem. Let's suppose there is an equation ax is congruent to b mod m. Okay, you know the value of a. You know the value of a. Okay, you have to find out how many different values of b can it take. Okay, for an example, let's take an equation like 2x is congruent to something mod, let's say, uh, 4. Okay, so I can put x equal to 0, right? X equal to 0 will give us 0. Okay. X equal to 1 will give us 2 into 1, 2. X into 2 is going to give us 4. If you put x equal to 5, so x equal to 3, it will give us 6, right? And if you take a remainder with 4, this is nothing but 0, 2, 0, 2, right? So the different values that you can take over here, you can continue, it will just give you the same thing. You can only take 0 or 2, right? You cannot take the values 1 and 3. Even though remainder with 4 can possibly give you 1 and 3, you can never get that. So the question is, given the value of a, and you have an equation ax, right? How many different values can it take? Okay, out of the m values that are possible, 0 to m minus 1. Okay, pause the video right over here and think about how do you go about solving this. How do you think about this? Okay, and I'm assuming that you have done it. Please do it if you have not. It's very similar to what we have been doing. The way to go about it is, I hope you have done it now, right? So ax plus some y times m is going to be equal to b. We have to find the potential values of b. Okay, and for this the only condition is gcd of a comma m should divide b. So what we can say is, hey, as long as this divides b, we are good. So in the range 0, 1 up till m minus 1, whichever numbers are divisible by this number are possible. So what you can get is, hey, I can make 0, I can make GCD of a comma m, and so on. So in fact, in this case, you can see that a was 2, m was 4. So you can take any number which is divisible by 2 comma 4, which is nothing but 2. So every multiple of 2 was possible in the range 0 to this. So 0 to this, every multiple of this is possible. So the number of numbers that are possible is nothing but, there are m numbers divided by every, in the interval of this you are getting different solutions. So GCD of a comma m. These many values are possible to be taken by the value b. Okay, and in fact this is always divisible because it's a GCD with m. So whatever this number is, it divides m. So it will divide this number. So it will always get a solution. Okay, these many valid remainders are possible for the AX equal to AX equation. Okay, okay, that's another thing. Let's try to move into another next level thing, which is Chinese remainder theorem, right? I think there is a theorem which tells you, hey, if you have bunch of equations, a1x is congruent to p1 mod m1, and there is the same x follows another property, ax is congruent to b2 mod m2, right? And there are more such equations, let's say, right? More such equations. You have to find out an x that satisfies all these equations, right? It's sort of um, like simultaneous equations in normal like mathematics, and convert it to a modulo domain. That's how this can be thought of. Okay, so this is what we are interested in. How do we find out a solution for this? So the way to go about this, let me in fact show you this same thing in the CP algorithm blog so that you guys get an even clearer idea. So there is this Chinese remainder theorem that we are talking about. Okay, so basically we have to find an a that satisfies these things, and of course we can just make all of these a1 move to this side by multiplying a inverses. So one thing that we can easily do is like maybe multiply with a1 inverse and then multiply with a1 inverse, right? And just get these things removed. Inverse into the same thing is 1, so we can get equations like this. But anyways, let's keep it this way only. I don't care about it. Okay, let's go back. Let's try to think about it from first principles, right? Let's try to think about that way. So this is the set of equations that is given to you and we need to solve it, right? So basically what we can do is we can try to get an equation. Let's say these three are there, solve the first two and get a general equation, then solve the next with the next one, then get a general equation, right? So this is the general form that we want to solve. Okay, and in this case there are multiple cases. One is like they are all like co-prime, there are prime numbers, and then there is a general version that you can kind of get into it, right? For non-co-prime moduli. So the co-prime version is simpler, non-co-prime is a little difficult, but we'll not think about these things too much, right? We'll kind of go from first principles, like we know just ax plus by equal to c. How do we get a solution for this, right? So okay, let's think about just two equation, because whatever satisfies this, let's suppose we get some x is going to is going to be equal to some number mod some number. Okay, this is what we will get, and then you will combine it with the next equation to get another equation. We'll combine it with the next thing to get it. So as long as you can combine two to get a final equation, you are good to go. Okay, that's how we generally solve these problems. So we are given a1x is congruent to b1 mod m1, a2x is congruent to b2 mod m2. Okay, I'm gonna forget about the rest of the equation, and you want to combine these two. Okay, okay. So this is going to give us a solution in the format x is congruent to something mod something. Okay, let's try to think about, hey, what is going to be the value over here, right? What's going to be the value over here? I mean, why not just m1 or m2 or anything like that? Because the problem with this is like this x is cyclically repeating itself after m1 values, right? M1 as a value. This is cyclically repeating itself after m2. So if something is repeating after m1, if something is repeating after m2, when you combine them, right, the value after which it will repeat is nothing but LCM of m1 m2. Okay, this is the minimal repetition period, right? I mean, think about it. It's like there is a clock over here which repeats after, so this there is x m1 number of like spokes over here, so in every second it goes in one of the clocks, and over here there is another clock which has m2 number of spokes, right? 0 1 2 3 up till m2 minus 1. And if you increase, like you can try and increase this by 1, then this one, then this one, and this one, like every second increment, every plus 1 you do it on this side and you do it on this side also. So it will turn out that, let's say, after m1 time it will come back to this 12, but in m1 time this will not come back to 12, it will be somewhere over here maybe, right? So after LCM of m1 m2 it will actually come back to the same original point for both of them. Okay. After m1 into m2 definitely it will happen, but you can also divide it by GCD. That's, and there is this formula, right? LCM of m1 m2 is nothing but equal to m1 times m2 divided by GCD of m1 m2, right? So from this we can get, and this is going to repeat after LCM of m1 m2. Okay, but we want to find the solution for this first of all, like that's more interesting, right? LCM we can say, hey, it's going to repeat after this much, so let's take LCM of m1 m2. What's the value after which it will repeat? First of all, they should be individually solvable, and there are certain criterias for that, right? Like this individual equation can be written over here as a1x. I'm just taking it as plus y times m2 m1, right? Because remember the same step, just take it on this side and plus my m1. We have done twice right now, right? This is there. To have a solution for this a1 m1 b1, we have to have a equation that, hey, GCD of a1 comma m1 should divide b1, right? So that it's possible to be solved. And if it is dividing, then we can find a inverse, like when this divides this, right? Not really a inverse, we can find a solution for this and we can get the answers for it, right? Okay, now for a2 x plus y m2 equal to b2, you can again do the same check if it's possible to solve it or not, right? So now we have basically two simultaneous equations where you have to solve and get an answer for this. And note that over here the remainder was m1, over here the remainder is m2. So x is same, x is remains same over here, but this is going to be y1, this is going to be y2. It's not the same, because there would be some different multiple of m when added subtracted from a1x will give us b1. There would be some different multiple of m when added subtracted with a2x will give us b2, right? So this will be y1 and y2. It's not the same thing. Now this is the two equations. We have to find out the value of x, and how do we do that? How do we find out these things? Okay, that's pretty interesting. Let's think about it. Y1, y2 is there. Okay, so maybe this x is common, so we will like kind of find out the. We'll try to eliminate x from this side. So what I will do is I will multiply this equation with a2 and multiply this equation with a1 and then just get the subtract it. So y1 times m1 we multiplied with a2, okay, minus we are subtracting this equation, so a2 a1x a1 a2x they will get cancelled off, minus y2 m2 a1 is equal to, we are multiplying this whole equation with a2, so remember b1 a2 minus b2 a1, this is what we will get out of as an equation, right? And note that we know the value of m1. So what are knowns over here? M1 a2 you know, m2 a1 you know, b1 a2, these all things you know. So it is like some different y1 times this term over here, okay, minus y2 times, I'm going to just write plus minus what is going to be over here, uh, m1 m2 minus a1 m2, there is some constant. Okay, so this is how you can write the equation. And now if you see, this is nothing but two variables, right? I can write this as x, I can write this as y, some y, I don't know, but and this has some capital A, this capital B, and this is capital C. There's nothing but ax plus by, these are knowns, right? A, B, C are known, and then this is nothing but ax plus by equal to C, right? That's how this particular equation is going to look like. So I can always find out some solution for y1 over here. I can plug in a value of y1 that will satisfy this equation, right? We can do the checks and stuff and we'll get a solution for this. Just plug in the extended Euclidean GCD and you will get the value of y1, right? Something over here, right? Okay. Now, once you get that, we can try and solve the GCD. It will be in the modulo. What will be the modulo for this one? Like, you will get the absolute value of y1, right? This is going to be give us one absolute value of y1. And there are multiple solutions, but we'll just take the absolute one y1, whatever y1 satisfied this. And we can plug it back over here to get one value of x, right? If you get the value of y1, you can plug it back over here and you can get one value of x, right? Because whatever y1 comes over here, it is going to satisfy this equation, right? We came from there only. Just plug it in over here and you will get the value of x, and that's an x that satisfies this. So if you get any one solution of x over here in the equation, then plug it in y1 over here and you will get the value of x. Like, it will be divisible. When you move it this side, this will be divisible by a1 because we have taken the equations that way, and then you will get the value of x. Okay, so you will get some x dash mod this from this. Okay, and that is going to be one of the solutions of this simultaneous equation. And like, every one of them is going to repeat after LCM of m1 m2 number of times. So from these two, you will get an equation. Hey, this is going to tell us, hey, x is going to be equal to x dash mod m1 LCM of m1 m2. And again, you can combine. So this is the x is congruent to this, and then there is another 3. A3 x is congruent to whatever this is, some b3 mod m3. So what will happen is, you will take, this is also like something like 1 and this is some other number, right? X dash, so it's a number. So this is so this is b dash, a dash, this is m dash. So you now know an equation to combine a, b, m values with a, b, m values over here, right? You know how to combine them. Just combine them again and you will get the new value of x congruent to something mod the LCM of three numbers, m1, m2, m3. Okay. So with three equations also you can do this. And generally, like, if you have multiple equations, the way you will get it is x is going to be congruent to something mod LCM of all the like this. Okay, and you can just solve two equations at a time to get this. So basically, whatever we get over here, x repeats after LCM of this many number of times. That's what this says. Mod is remainder. Remainder means it repeats after this many number of times, right? This number of times. Uh, okay, so that's a general way to solve the, like, Chinese remainder theorem equations. Okay, let's go back to the blog and let's have a look at what like, as an algorithm exists for this. There's something called as Garner's algorithm, which solves this very neatly for the general purpose. But you can also do it from first principles, right? Okay, so this is solution for non-coprime moduli. So for the coprime ones, you have a very simple solution like this. There is an equation which says that, hey, m1 is nothing but a product of every modulo, in not including it. And you can try and find out this equation. This is a solution for this. This is always known solution for this. That, hey, multiply it with that. Where is this? Yeah. So we are trying to solve this, right? So we know that the solution exists like this. Okay, let's n1 be the inverse of m1 and the n2 be inverse of m2 mod n1. If you can find these two numbers, okay, these two numbers should exist, then you can get a general value like this. This is going to be always true. Yeah, this is the final equation. Since n1 m2 are co-prime, the LCM will be product only because GCD is 1, and then this is the solution for this. Okay, this is how you can think about it. Okay, so this is there as a nice idea. So you can use extended GC algorithm on this particular equation itself to get the inverse for m1 and n1 both simultaneously. Right? Okay, so this is how you solve Chinese remainder theorem for coprime cases. For non-coprime, there is this algorithm called Garner's algorithm. I'll go to that blog real quick, right? Which is basically to find out with certain amount of precision if you want to do that. For our cases, we don't need this mostly. But now there are like these good problems. These three problems are really good. This is what I would be giving you as a quick home task after this particular video. that if you have understood this, go ahead and solve these three problems. They will give you a lot of clarity on how to solve it, right? How to solve questions of this. This remainder game is a very nice idea. I know this. This is like, this uses the property of, hey, when is things gonna be common with C1, C2 and stuff, right? You have to know about that, and you have to think about the Chinese remainder theorem. Plus, it requires a little bit of sieve and stuff, so you can go about and explore that. Okay. So this is the place we'll stop for this particular video. And I think we have talked about many theoretical things in the last two videos, right? Maybe from the next video onwards, we'll like write some code and solve problems. But for today, like go ahead and solve the problems that are listed in the CP algorithm logs for these two topics, like the linear equation kind of topics, modular inverses. Then the next one was linear congruence, and the next one is Chinese remainder theorem. Solve the equations, solve the questions of those, and then you will get a good clarity on a lot of number theory problems. I think till a certain level, like 1900 or 2000 level, you don't need any number theory more than this, right? You should know about Chinese remainder theorem, but that's it. That's the limit where you have to be at. Let's suppose you want to go beyond that for like very hard problems for world finals and all. Then you need to go into things like, hey, how do you find square root? How do you find log? Like there is something called as baby step, giant step algorithm. There is something called as Tonelli-Shanks. There are multiple different algorithms that kind of solves problem over there, right? In those ranges, right? Talking about legend trays and other things. We don't want to get into that complex maths as of now. Okay, so this is the place I will stop for today, and I hope you got some value out of this. If you did, just do press that like button and like make sure that you subscribe if you have not, because these support me creating more such videos, right? uh, that's going to be a wrap on the theoretical number theory. Maybe we'll take some problems in the next few videos, or we'll do some mixed problem solving, right? Let me know in the comments what do you want from me more on this channel, and I hope you are enjoying the channel, right? Thanks for watching this particular video. See you all in the next one. Bye bye.